Welcome everybody. Please take your seats. We're going to begin this afternoon session, which is devoted to JPAS synergies. We are going to begin with Matthew Malkan, who is going to tell us about observing cosmic evolution of dust from space, from Akari to James Webb Space Telescope. Thank you, Matthew.
Thank you very much. I came here because I wanted to learn as much as I could about JPAS, and I must admit, the information, it's getting so exciting, everything that I'm learning. But in particular, I mean, the number of people who are working on this project, who are really very good, it's a little bit intimidating, the thought that I could collaborate and have something in addition to contribute to all of these other excellent astronomers. But, I think part of the reason I figured out what this might be, I realized, it's my name. My name, it only has 3 syllables. Many of the names of you people in this room has more words in the name. I mean, it's kind of like to me, it's like a meeting of Spanish, well, sorry, not the Spanish, it's like the aristocracy is meeting here. And so, but I have a solution to this, it's no problem here. I'm going to now change to use my full name.
There you go.
And I feel much better, more at home with everything else now. If that's too complicated, you can just call me Matthew Arnold. I don't know, the graduate student who is just about to finish, who you will be seeing her work from UC Kim, I don't know what she's going to do about her name. We can discuss.
Have your mom's surname, and that will give you all the length.
Okay. Good. My job is to make the case to justify the title here that the Akari North Ecliptic Pole field has unique importance that I think it can only really be completely successful in a collaboration with JPAS. Just to remind you, Akari, that's the Astro F satellite of Japan, very, very successful. It's now completed its mission. Maybe not that many people know about it, so I'll be telling you about this. And in particular, you have the same situation with satellite after satellite. The true North Ecliptic Pole is, of course, the only place that any satellite, it's always 90 degrees away from the sun, a very favorable place to look for. It was a very strong reason why much of the Akari cryogenic mission was devoted to looking at the North Ecliptic Pole and then some of the South Ecliptic Pole. The result of this is like a unique legacy, about 5.5 square degrees, and it is at the true North Ecliptic Pole. And what's unique? The infrared camera of Akari has 9 filters that cover the entire 2 to 24 micron range. And so you put these 9 filters together, and you basically get a very crude infrared spectrum over that range. And this just happens to include many of the key diagnostics of dust. If it's warm dust you're looking for, PAH emission falls in there, even silicate absorption falls in there. And I must stress that this is the only field that will be available with these kind of infrared spectra for thousands, tens of thousands of galaxies in the mid-infrared. I said for the foreseeable future, I mean forever. I just don't know when it's going to happen. Again, I mean, the alternative would be to use something like JWST to look at one galaxy at a time instead of tens of thousands. So anyway, so this is it. Now, that's a good reason this is an important field, but it's not just that. Of course, we knew the importance of this, so we have hammered this at every wavelength known to astronomers. And this table wasn't even long enough. I ran out of space there. I mean, every wavelength you can think of has some of the deepest, or maybe the deepest, as deep as any data you want to have. So that basically every one of these Akari sources, we can tell you every wavelength. And this thing is the timing. Okay. But of course, you know what always the problem with is the follow-up to really do the science is we have very few spectra. relatively few. We've been working at it very, very hard, but I can see, of course, as you know, we're never going to get actual spectra for more than a small fraction of these. And this is already clear. I mean, we keep going back. The time assignment committees have basically said, okay, you guys, you have a lot of spectra. It's incremental now. We're not going to give you all of the telescope. Anyway, so that's where we are. So basically my conclusion from this, and it's very clear from this week, is the only JPAS, which really has spectra, basically can say so much of the potential of this field. But I'm going to show you some of the things that we were able to do so far. Let me just remind you where the North Ecliptic Pole really is. A little bit of confusion about that. There's the North Ecliptic Pole, and you can see that it's actually at 270 degrees in RA, right? That's the basis of the equatorial coordinate system, celestial coordinate system. And so, in fact, the JNEP is, this is about to scale, tried to make it to scale. It's about 10 degrees over to the west there. And so we know we'll get beautiful JPAS data here. I'm trying to really persuade you strongly to get beautiful data just over here also in this area. I'm not even showing you all of the different footprints of all of the different instruments. Renato had a really nice slide, showed more data on it. And I'm very encouraged by this meeting, but well, for example, Alessandro gave me very much encouragement. The 10 degrees is no big deal, I think is what he said. Okay, so what can we do? Again, I have to explain some of the science, what we will be able to do and are doing with the infrared camera. So here's what's special about it. Of course, Spitzer, we all know Spitzer did a wonderful job. Some fields, but of course not all fields. When Spitzer was cold, it was able to do all of these filters here. And you notice there's an enormous gap right here. Nothing in between here, but this gap is very nicely filled by 3 filters in the Akari infrared camera filter set here, 11, 15, and 18. So basically this Spitzer gap is what I'm calling it, that we now fill in. That's where the most interesting dust features that we want to study all are falling, really, for all registers of interest. So let me give you the prime example here. Everybody knows, in case you forgot, there is some illustrations of some typical PAHs. That stands for an abbreviation, polycyclic aromatic hydrocarbons. So that means we have all of these carbon rings with hydrogens around them. You could either call them very, very large molecules or very, very small dust grains. And this seems to be very common and very popular throughout dust in the universe. And so why is this so important, as you know? Well, consider an ultraviolet photon comes in, and then when one photon is absorbed by one of these little dust grains, that's so much energy that it begins to, it's spread around the molecule or the dust grain, and it heats it up enormously to effectively thousands of degrees as it vibrates. And so there are stretching modes of carbons and hydrogens and bending modes, and what do you get? Then the energy is going to come out, a lot of energy, amazing amount of energy is going to come out in the mid-infrared. That's really where, and there's a small weak feature at 3.3 micron. And so it's a spectacular combination of features from for the modes of the dust grains. Particularly, notice the strongest one here. This is an amazingly strong complex around 7.7 micron. In fact, that is, I believe, the strongest spectral feature in the entire spectrum of galaxies. I think it's right. It's more than 10 times stronger, for example, the strongest emission line, which is H alpha. So that's so strong. Can you pick up the detection of the PAH emission in the filters? The combination of the 9 Akari filters? That's the question, and I'll show you. Well, the answer is absolutely yes. And so now how do you do this? it's pretty obvious. Here, look at the purple circles there. It's all of our multi-wavelength data for some random galaxy at a redshift of 0.36. Even the far infrared is included there, optical, ultraviolet, and so forth. But you need to concentrate in this mid-infrared region where we have this Akari infrared camera data. And the first thing you notice, okay, what you actually do is you take, in Sigali, it takes a model of the PAH dust spectrum, and then it convolves it with the band passes of these filters. And you see that the filters which fall at the top of the 7.7 micron feature are very clearly elevated. I mean, you can clearly see it. You don't really even need a computer to tell you it's there. So here's just a typical example of a sort of a normal strength. These filters are definitely elevated over the other filters that don't lie on the PAHs. And this is a fairly normal strength, okay, in the strange units that I guess was defined by Bruce Drain. We find 6 or 7% of the dust grains are in the form of small grains, PAHs there. And just to show you that we have some dynamic range, here are two galaxies below here which have a similar coverage, much weaker PAHs in these cases, just a little bump there and there. And in fact, here's a galaxy where there is just upper limit. There is no PAH at all. So you can see some differences here. And it really doesn't matter what the redshift is all over the range of interest, 0 to maybe a redshift of a bit more than 1. We have filters to cover these things. By the way, this last galaxy over here, also Sigali has included a substantial contribution from an obscured AGN, as shown by this orange line, which is making a lot of the mid-infrared emission. I'll come back to that in a minute. So you have all this information here. All right. So now I'm giving you results of Helen's thesis. This is why she's going to very soon be Dr. Helen Kim, very soon. But if you might be worried, we were very worried. Okay, do you really trust these PAH measurements from filters? You know, that's a model of a fit. Give us a truth set. We have a truth set. The truth set is that also in the NEP region, there are a series of slitless infrared grism spectroscopy. It's called SPICY. It's a terrible acronym. And in fact, I'm sorry, I'm really getting ahead here. The spectra we published, the first author is Oyama is already a collaborator in the JPAS group. He's a really good guy. And we were very happy that he has a spectrum, that's the truth, that tells the actual luminosity pH, agrees beautifully with what we determined from our filters with Sigali. So now that we really have a lot of measurements for the objects we're not going to get infrared spectra ever, for thousands of objects in principle there, let's think about what it's useful for. We're expecting that PAHs are produced by ultraviolet photons. Ultraviolet photons come from young stars, recently formed stars. This is thought to be a potential, or should be, an indicator of star formation rate, regardless of what obscuration is present. It doesn't matter. We're looking in the infrared, in the mid-infrared. So we should be able to find any kind of obscured star formation if it's present. All right, it works. Okay, here's the evidence from Helen's thesis that it works. We're comparing this new obscured star formation indicator, the luminosity of the 7.7 PAH feature, against the sort of traditional classic H alpha luminosity. It's supposed to be counting the ionizing photons from O stars. Of course, it has to be corrected for extinction. We do the best we can there. I mean, if this is available. And all right, it's a beautiful correlation. In fact, there's even some subtle point here. These are sort of normal star-forming galaxies here, or less than normal star-forming. These blue galaxies over here have an enhanced star formation compared to their stellar mass there. So we would call these more starburst galaxies. And if you look really carefully, Helen has found that they have slightly weaker PAH for the amount of star formation. But anyway, that's a subtle point. These are very extreme starburst galaxies down here. Perhaps, I don't know, maybe it's such an extreme high radiation environment, maybe some of the PAHs could be destroyed in that case. But anyway, I think that this is very prompt, very happy. We're very successful about that. So we have ways now of getting obscured star formation. I don't care how dusty the galaxy is. Now, what galaxies are we looking at? Well, here's some of the Akari NEP galaxies. And so I said that we have a range of star formation rates. These are estimated from looking at the multiband data compared to the stellar mass. At the low redshifts, you have galaxies down to fairly low masses, the full range here. As you get to the higher masses, we have more luminous galaxies. You'll notice that we have the I hate this term, the main sequence of star formation rates. But anyway, we have a lot of galaxies. We have galaxies below it here, which also have pHs. And we have galaxies, especially at higher redshifts, which are above it. These actually turn out to be very important galaxies. So we have these. Of course, you'll notice most of the points here actually are black dots, which means no spectral information. In fact, the only reason we put them on the plot is we're using our rather crummy photometric redshifts based on broadband data. So that's a limitation, but what can you do? So just to give you some flavor for the importance, why we really want to get the obscured star formation here, right? And we have optical astronomers here. Well, why do we care about this? There's so much of it. So if you look, for example, at luminosity functions, that this I think is from Akari NEP data, this is the infrared luminosity that we can determine. It's gone up enormously from the current epoch to redshift of half to a redshift of 1 here, right? It sort of looks like the entire luminosity function is shifted to higher luminosities by about a factor of 10 for your typical galaxies over this redshift range. So there's been an enormous cosmic evolution. Something quite dramatic has been going on with these galaxies. But here's the important point, and maybe it won't surprise you to know this, but all of the traditional studies that have been done by optical astronomers, they're basically using rest-frame blue or ultraviolet emission, but that is only telling them about the unobscured star formation in these galaxies, and I want to show you it's missing most of what's happening. So here with our data, what we've been able to reconstruct so far, we've integrated the luminosity functions in the Akari NEP. You have to do some extrapolations. The number statistics really are. We want to make it much better. Here, look at the lower line. There's your traditional ultraviolet-based luminosity function, and you can see it's going up as you go back in time to higher redshifts. But look how small that is compared to the total star formation rate that we're estimating here using the infrared and these models and so on. This is mostly obscured star formation. At the higher redshifts, it's different by a factor of 10. That means that the traditional UV methods are missing 90% of what's actually happening there. It's shocking. Interesting also, we've divided this into the starburst is shown as star there, and even though they're not so numerous, they're actually substantial contributors compared to the more normal galaxies. They've become dominant actually at the higher redshifts. That's interesting too. I mentioned before, what about AGN? Of course, we're very interested in finding AGN, obscured AGN as well. How do we do it? Several ways. There are many ways. We want to use all of the ways because they give you different views. For example, here's another Sigali fit, like one of the ones I showed you before. And you see this very distinctive, strong warm dust component. It makes this really strong mid-infrared continuum. It's fairly straight there. It's modeled with this green curve from Sigali of an obscured AGN. It's producing quite, 27% of the mid-infrared luminosity, just to show you that you can see the difference with your eyes. You don't really have to have a computer. Here would be a normal galaxy that doesn't need the green component. There's no evidence of any AGN in this galaxy. All of this is just coming from PAHs and cooler dust in the galaxy. Of course, if we had the spectra, we have some spectra, then we could compare to emission line ratio measurements. Here's a classic BPT diagram where we can pick out some AGN that have a high ionization emission lines. That's an interesting way. And you could use some color selection. And all of these different selection methods are overlapping each other. They're different ways. We also have X-ray data. But none of them really gets the full picture. X-ray data, X-rays can be absorbed and so on. And, so each one of them has advantage. I think what's really powerful, if you really want to get the picture, I want to have all of them. together to compare. And that's what we can do just in this field only. All right, here's a funny one. This is an AGN. I just wanted to point this out. Look at this AGN. There's a strong component there. It's this orange component here producing a lot of the mid-infrared light. Look at this 15 micron filter. Yes, that's one of the Akari filters. It's so low. I wonder why it's so low. It just happens to fall at the observed wavelength where the rest frame 10.6 silicate absorption, that is the strongest absorption you get, it takes a lot of dust to make such an absorption, appears to be falling. And this is a deeply embedded, heavily dust obscured galaxy that we found just photometrically. And again, there's no other way to discover these galaxies. You know, they were found with some spectra, when Spitzer would look at one galaxy at a time, and JW, I'm sure we'll find more. They targeted Euler's, for example, and you do find this kind of behavior. But now we can find them in a representative, complete, comprehensive sample of all the galaxies in the universe at, back to maybe a redshift of 1. So just, okay, we're trying to do other things. I'm just now I'm getting to some things which you don't really have to believe. We found AGN, we found these other things. We tried to find clusters of galaxies. And each X here represents a region where we found a few dozen galaxies. We thought it had the same redshifts, but these are not using actual spectral redshifts that you can believe. They're photometric redshifts. So this has to be done properly. Okay, so 20. Okay, I'm okay. So but it gives you an idea. And I think that again, we're stuck right now until we have JPAS. Then there's so much interesting questions about the environment that we've just been waiting to have the chance to look at that with all these data and the infrared. By the way, this just again, that shows the Akari footprint is in orange, and then you have some other footprints here of Herschel and so on. So that's about the size of the field that we have at the moment. But actually, it's in some ways it's going to be getting even a little bit bigger. I mean, let's just look for a minute. Suppose you think, well, that was kind of interesting. Maybe it's a nice field and so on. Even if that's not persuading you that this really is important for JPAS, consider now the future. The future is all with the North Ecliptic Pole field for the reasons I said. Okay, we're going to ignore that message. And the reason for that, again, it's sort of dictated by how satellites work. Like, okay, look at this. So I guess I'll start. Well, this is all really motivated by Euclid. Euclid has defined its legacy deep field. I guess, there are two of them, but anyway, the big one here is in the north. Here's the footprint of it, because this is just the easiest thing for them to observe all the time, over and over again. And it's really quite nicely matched. Okay, it's a little bit bigger than our area. So in anticipation of that, fairly at the end, the last 2 years of the Spitzer lifetime, it's warm Spitzer, they devoted a legacy program to spending, basically covering this region here, 6,000 hours of warm Spitzer time was put in this region, no other region on the sky. And motivated by that, some of the same people, we're all friends and so on here, some of them are from Hawaii, have been hammering a 10 square degree field. And for reasons having to do with a stupid television show, it's called the H2O survey. And they're just pouring an incredible amount of telescope time into this, starting with a Subaru Hyperstream camera. We've already covered the inner part of this region. Now we're going to cover more of it. I mean, 30 nights on these big telescopes to do this. It's incredible, and there's much more. Just to give you a feel for what we're getting now, we'll compare, well, what was done before? There were other deep fields and so on, maybe not really the same. Well, if you look at this little teensy square here, all of the different famous deep fields, you have Goods North, Goods South, all the Hubble deep fields. Those are these little patches here. That's all the deep fields that anybody's really ever going to get, So if you're concerned about, cosmic variance, statistics, really learning about the universe, you've got to go this way. And so my conclusion then is, I hope I've tried to make the case that please include the real North Ecliptic Pole region, this legacy field, in the JPAS survey to get as good deep data as you possibly can. And I would say that this will give us the seeds of wonderful science. Okay, it's a little bit of a pun, and I'm really excited then about the chance to collaborate with people here. Oh, yes.
Thank you very much, Matthew Arnold, for your.
He's the first person who's called me. It sounds good.
Now you're in nobility, so.
Yes, Renato.
Very fast question. So you say you tried to find clusters. Was the Chrysalis, not supercluster in there?
Well, I think it is one, I think it's in there. What I should do, of course, is look at it as a redshift of 0.087. Yeah, I'm going to go back and do that. That one I might believe,
Okay.
actually, but well, I mean, I can show you our photometric redshifts. They're what you can do with broad bands. If the uncertainty is 6 or 7%, and we have a lot of outliers and so on. I couldn't tell you which objects are really in that supercluster and which ones are not. I just have some candidates that might be.
Okay.
Yeah, I mean, there might not be hundreds in there. Yeah. Yeah, so we have a large number of candidates, but I just don't believe them.
Raul?
Hi, I have a question about QSOs and AGNs. When we looked at WISE, for instance,
Yeah.
as a tool for helping detect AGNs, it does help a lot for shallower surveys like JPass and so on. For JPass, it will also help, but this is, of course, much deeper. I wonder, in pretty much, and it covers a wider range. What is the size of what is the astrometry in that case? Because WISE, one of the issues we have there, sometimes source confusion, because depending on the band, it's like a few arc seconds there. So for Akari, what is the typical astrometry that you get for your sources? Does it depend on the filters? Do you recall that?
Well, so the Akari, of course, is a small telescope. So at the longer wavelengths, the PSF is several arc seconds. In fact, it's a little worse than Spitzer. But of course, the longer wavelengths are matched to the shorter wavelengths, so they're all detected.
So you have several measurements of the same thing.
And so then it's, as you know, it's a multi-step process. So we also have a very excellent ground-based near-infrared photometry, and the whole field is covered with hyper supreme cam, which is sub-arc second seeing. So if you believe the identification of the source, then I think we have sub-arc second accuracy positions. And of course, we know, and this is important too, we know where there are multiple sources on top of each other, and to watch what we know. So we're not going to get tricked on those. WISE certainly is good. It's not as deep as Akari does, and of course it just has a few filters, so but it's nice to have it.
Thanks.
So there's a question from Chris in the Zoom.
Shoot.
Yeah, so my question is, what is the redshift that you're clustering up in the NEP?
What is the redshift of the supercluster? Okay, so
Yes.
0.087. Is that right? Yeah. So it's I mean JPaS it should just get definitive result for that.
Thank you.
Can I show again the plot of that one?
This one.
No, the previous one.
Previous
The
one?
cosmic star formation rate. Yeah.
Yeah. Okay. Thank you.
Okay. Because I tried to compare with another result that we have already from JPaS, where we just comparing the cosmic star formation rate derived from H alpha with respect to
That's interesting to
with
do.
respect to the
That-
continuum.
Might be somewhere in the middle. I don't know. Again, it depends on how you correct the H alpha for extinction.
Well, we correct for distinction, but based on the H alpha, H beta ratio.
We've tried that and it works sometimes. Yeah.
Yeah, well, I was trying to see if the number is more coincident with
Okay,
the
I would like to
H alpha
check.
or with the continuum.
Yeah, I very much want, let's look at that. Okay, yeah, I mean, that's a good thing to do. Of course, now, we didn't have H alpha for a lot of our objects. Now we stand the chance to have.
No, it's because with the same data, I mean, it was with the JPAS data.
Yeah.
We
it's great.
just found a difference between the star formation rate density if we estimate from the continuum and the star formation
That's
history
very
of the
interesting.
galaxy with respect to the H alpha. So I was trying to figure
Okay,
out.
that's very interesting to track that down.
Yeah.
So do you have a feel also on this, but which galaxies, in terms of their stellar mass, are the dominant contributor?
Yeah,
to,
that's That's a very good question. So if I go back to these luminosity functions, there's sort of a curvature in it. So the typical dominant galaxies will be somewhere around the knee of the luminosity function. So, okay, this is infrared luminosity. So so it starts out being less than 10 to the 10 solar masses, and then as you go to higher redshifts, it gets to be more closer to 10 to the 11 solar mass are dominating those dusty starburst galaxies, which is kind of lucky because that's where we can see. So we can see the galaxies that make the most difference, even if we can't see the faint.
Some kind of exposure estimate to really, detect all the costs for.
Well, we know all of the optical magnitudes for all of these galaxies now, and of course, there are a lot. I mean, I worked out how many thousands we're going to get. The best data, of course, are on the objects which are brighter than 22. I mean, there are. If you want to go to the higher redshift and do the fainter objects, of course, we've been working on some galaxies at 24, which I guess probably I don't know what we can do with. So just go as deep as you can possibly go here, but already I know that we're going to have thousands and thousands of matches. JPAS Akari counterparts.
Very small one.
Just based on what I saw so far.
Yeah, great talk in general. Just a curiosity. For the pH part of the SFR, did you have to get rid of the metallicity for the...
Okay, I'm glad you asked that. I didn't have time to mention it. There is, I have a slide somewhere of this. There is a metallicity effect in there, which is subtle, but again, we're suffering because we don't really usually have the emission lines. JPAS can give us an estimate, oxygen 3 and so on. And then we would be able to correct for that because the effect goes in a way you should not be surprised. The galaxy of a given star formation rate and other given properties, if you lower the metallicity significantly, it does appear that the pH has become a bit weaker compared to what they were for solar abundance. And so that's an interesting effect, and it's real, and we've measured it and we're aware of it. So yeah, to do this properly, we would like to have some estimate of metallicity.
But it's more or less relatively small, or what do you think?
Yeah, it's sort of like this kind of shift. Yeah, maybe, yeah. So 30% kind of thing. Yeah, so again, it's another reason why you really need to have spectroscopic information to do this work properly. Really glad you mentioned that.
Well, let's thank Matt again.
Thank you for the opportunity.
Rolf, you can
Yes,
change your screen if you want. Yes, we can hear you.
okay, I'm trying to collect my window.
Yes.
Um,
In the meantime, I remind you, I will make you some kind of sign when you are on the 20-minute mark.
Okay. Do you see any of my screens right now?
Not yet, just the tiny window with your name and some beautiful image of a galaxy.
Okay, let's see.
Doesn't look like you've started sharing yet.
Yeah, when I open my share window, I don't actually see any of my windows appear.
So not here either.
When you choose share, try to share the whole desktop.
Yeah, I only get use system capture and whiteboard. I've never seen that before.
It's one of the options, but
Yeah, I think you have to use the cap. That's with the new update of Zoom.
Am I saying try to use the caption one?
Yeah, you have to capture the screen you want to share. The portion. of the
Capture
screen.
the portion of the screen that you want to show us.
Okay. It does not seem to capture anything. I do apologize.
Oh.
when you click on share screen on the green button, what do you
Yes.
see? What are the options that you have?
I see only two options. Use system capture and whiteboard.
Then choose your system capture. Click on that.
I'm trying to click on it, but it is not doing anything.
I have no idea. This is not my.
Le voy a mandar la presentación a alguien que esté conectado y que la comparta.
Okay.
Your presentation, do you have it in PDF or something like that?
Yes, it is in PDF.
Okay. Do we have one volunteer in the virtual audience that would like to share the screen if Rolf sends the PDF to him or her?
No answer.
No answer.
I can do it. Send me. This is Luis.
Okay.
What email address can I use?
Put it in the chat.
Yes, if you
Put
in the chat would be more easiest. If you agree, Rolf, can I start with the next talk and then in 30 minutes we go back to you?
Yes, I do apologize. I don't know what's going on.
Of course, it's. I mean, we can't fight these things. It just happened. So, in the meantime, while Luis receives it, let's move. If it's okay with you, Chris, to your talk. Chris, yes, that you are, and you are sharing your screen. Nice. So, after this tiny glitch, we will recover Rolf in a few minutes, but we move to Chris Willmer's talk. Talking about infrared imaging and visible spectroscopy. If you can make it full size, we are seeing.
Yeah, I'm just getting adjusted here. I need to do two things. So is this showing up full size?
Now it is, yes. I'll give you a sign at the 20-minute mark. Thank you.
Okay, thank you. So today I'll be talking about some work that we have been doing as part of the PEARLS survey in the NEP. It is a slightly different NEP from the Akari field that Matthew Arnold just talked about. Anyway, let's get into it. So this is an ecliptic time domain field, and it was selected by Rolf Jansen and Roger Winhorst, which would have been discussed by Rolf just before me, which is located in the JWST Northern Continuous Viewing Zone, which means that it's accessible at any time of the year using JWST. The reason it was chosen is that it has low galactic extinction and it has a low density of bright stars, which could have some nefarious effects on the JWST detectors, such as saturation and particularly persistence. So up to 2017, there were not many public data available in the TDF. There was the GALAX survey, there were SDSS imaging and a few spectra. There was Pan-STARRS imaging, 2MASS and WISE, a few pointed observations with Keck targeting mainly one object, and there were only 12 objects with redshift in NED, which mostly came from the SDSS. Of course, since then, there has been a really enormous increase in the amount of data, going from hard X-rays down to radio. And we do have a contribution in terms of spectroscopy coming from JPAS, which by now is the largest effort so far. And there's also spectroscopy that has been taken with Binospec and MMIRS, which has done here in Arizona. Before I go into the near-infrared imaging, I should talk about the Subaru hypersuprime camera imaging that was alluded to by Matthew before. This part was covered by one of the fields, which I suppose is part of the Euclid ground-based support, which has been PI'd by Günther Hasinger and Esser Hu, and it was observed in 2017 between June and August, almost at the same time that we started our near-infrared imaging. These data have been downloaded and reduced by Satoshi Kikuta, and we have imaging in the G, the I2 and Z bands, and plus 2 narrowband filters. These data reach considerably deeper than either SDSS and PAN-STARRS, and they have the advantage of having been calculated using Gaia DR2. These data have been extremely important for the TDF because they provided samples for spectroscopy over the years. They have allowed some of the photometric calibration, which I'll talk about later. And most importantly, the astrometric calibration of JWST imaging depends specifically on these data because the density of Gaia stars is really small in our field of view. To have an idea, this is a match between Gaia DR3 and the HSC data. We can see that the offsets are really small, and we have an RMS of the order of up to, about 180 18 milliarc seconds, which makes it really good, and it even allows for placement of NIRSPEC slitlets if one goes that route. So the near-infrared imaging itself, when we started this project, we did not have access to any facilities that would allow large coverage of the sky, such as CFHT, since Newfirm had been retired from the Kitt Peak 4 meter to give place to DESI. But being at Arizona, we have access to infrared detectors on the LBT and MNT, though because of the larger field of view of MMIRS of 7x7 arc minutes versus 2x2 arc minutes for Lucy, this made it the instrument of choice. And it would allow us covering the field with a mosaic of 4 pointings. These observations were taken between May of 2017 and June of 2019 and comprise a total of about 6,200 images. Of course, we had some challenges with this because imaging with MMIRS was a relatively uncharted territory. There had only been one publication using MMIRS photometry, and this was of an open cluster while it was in Magellan. And this meant that we had some idea of the exposure times, but they were not really well known. And it is very hard for you to characterize an exposure time with Q observations when you really need to have engineering data. So basically, we had to juggle the exposure time between having adequate signal to noise of sources against the sky background. We had to mind about saturation of bright sources, which would bring other effects such as crosstalk and persistence. And we also had to take into account the overheads when doing the instrument readout. Another effect which occurs with the MMT is a telescope jitter because the exposures have to be unguided. The reason for this is that the overhead require guiding buffers, and this would make any kind of near-infrared survey very expensive in terms of time. This gives us an idea of how the sky counts change as a function of air mass. And of course, here we have exposures which go mainly in the summer, which is the time when NEP is visible from Arizona, but it is also just before the monsoon when the weather tends to be really bad. We don't really have good seeing. But this gives us an idea of how the different sky levels for the different filters. And also shown here are the exposure times that we use. So some of the effects that I alluded to is on the bottom left, we have a histogram of the overhead in second per exposure, and this is all related to the readout of the detectors. However, this has improved significantly since 2019 because there was a change in the way the electronics are read out, so these are much smaller. On the right, we see one effect of the telescope jitter. Of course, this is a windy day, and this is taken in the J band, which are longer exposures. And because we're using a near-infrared detector, different from CCDs, we actually read out non-destructively. So you go accumulating charge on we call different on a ramp. So each readout differs from the other by about 4.25 seconds in this case. And we can see that the image of the star gets pretty elongated in some of them. And this means that very often you might have an image which is kind of elongated of stars. And on the top left, we see an effect of the crosstalk, the very bright source. And we also see a persistent ghost. So here what I'm doing is I'm showing two subsequent exposures, and the green shows the previous exposure. And these are things that have to be accounted for when doing the data reduction. So the seeing distribution over observations is shown in these two histograms. On the left, I'm showing the H in kind of pinkish color, J in green, and Y in sort of grayish color. And we can see that the best images are in the H band because these were taken when we were more experienced with the telescope. This was the last band to be completed. And on the right, we see the distribution for the whole filter. So in general, we have a seeing better than 1 arcsecond, but when making mosaics, I actually considered up to 2.1 arcseconds, which has some impact on the image quality. When this project started, we did have a material reduction pipeline, but it was mainly for spectroscopic data, and we had to adapt it for the initial reduction for photometry, basically doing the dark subtraction and creating slope images from the ramps. The reduction itself was based on Iris X dim sum, which can handle multiple dithers, the sky subtraction, and persistent masking, where for each exposure, because of the variability in the sky, you make a stack of the images in time to create a median sky, and then you scale all of these by the median value before you do the sky subtraction. Basically, what you're doing is having all these exposures have a median of about 1. Then this sky subtracted image is used to detect sources, and from these we create masks by extending the segmentation maps. We match the catalog with brightest sources of the previous exposure to flag ghosts due to persistence, and those are masked on the image corresponding to that object. And then we make a second pass to measure and subtract the sky background. Following that, we do the astrometric calibration using a combination of astrometry.net and SCAMP. I found that astrometry.net is more robust when you don't have really precise coordinates, but I stuck with SCAMP because of its ease in making the next step, which is the mosaics with the SWARP. This is developed by Alberto and at the IAP. And when making the mosaics, we use the same center and pixel throw as the HSC imaging. So this shows a coverage of the MU's photometry relative to HSC. So the big mosaic is a mosaic made from the HSC data, and the different coverage filters, J for this kind of grayish color, and in red is where the K band. And also shown is the present coverage of JWST that we have been taken over the last 6 months. The astrometry for the MUs is definitely not as good with as the HSC, and this is some of the crankiness that I find with SWARP. And we can see on the left that there are some poles in different regions, and this has the effect that I cannot create, let's say, I cannot use HSC as a detection image to measure the photometry. So we have to use other things when we want to compare want to make, let's say, an SCD out of the photometry. The photometric calibration used SCAMP. And the reason for using this is that SCAMP will actually examine each image and it will find from objects and from the offsets between them. And once you have all those offsets accounted for, then it will do the calibration using a standard catalog. In this case, it would be either pan stars for the wideband and 2 masks for the near-infrared bands. And the final calibration for the photometry was done using the Gaia DR3 stars, and measurements coming from Gaia, Sloan, pan-stars, and 2 masks, following the method that was described by Alberto Fernández for S+, where basically you create a grid of photometric points using the models by Paulo Coelho, and you convolve these with SCDs with the filter curves and a series of extinction values. Then you find the best fitting model for the stars using the reference catalog measurements, and then you use these stars to measure the offsets for each filter in the photometry to be calibrated. This was the way that S+ did a lot of their calibration in the medium band filters, which had no, let's say, comparable filter in the standard photometry. And basically, this is the method. Here I have the standard stars, which are fit by Paulo Coelho's models. And this is the case where I measure the star in the photometry, combining Gaia, Sloan, etc. And this would be the measurement in the K band. So this allows us estimating the offsets. Of course, differently from S+, we don't have thousands of objects to do this. We have only a few hundred, but still we can get RMSs of the order of 5/100ths of a magnitude, which is much better than we could do just using 2 masks alone, where typically the uncertainty would be of the order of 0.3 magnitudes. Another issue that we had to deal with because of not being familiar with the whole process of observing is that we had 3 different setups in the K-band imaging, which involved 2 filters and 2 gain settings. And we had to make these measurements uniform, and this was done using the regions in common between a gain of 0.95 electrons per RDU, which is a high gain, and 2.68, which is the standard one. And also we had AK spectroscopic filter being utilized in the first observations. The result of these is that we small significant, but they make a difference, and the corrections are less than 1/10 of the magnitude. And this allowed us to have at least a uniform K-band magnitude over the whole field. Though this does other measurements such as size related, these cannot be made uniform in the same way, and there are variations, and a lot of it's due to the seeing. In the case here, I'm using the total magnitudes as measured by Sextractor. Once I combine this catalog with the HSC, we can start making a star-galaxy separation. Given that the matches are really very good because of the good astrometry between them, the offset, the number of matches is very high within 0.8 arcseconds. Because of the seeing in near-infrared imaging, I decided to use the half-light radius as measured by Sextractor in the Z-band, which is a closest band. And this is the green line in the bottom of this plot. On the left, we see saturated stars or objects which have double images in them. And this is the bulk of galaxies. And this cloud of points to the upper right are objects without near-infrared, without HSC counterparts. And in this case, I'm using the near-infrared sizes. However, all of these were visually inspected to make sure that they're not due to noise or anything like that. And of course, some of these could be dropouts, which are just too faint to have been measured at high signal to noise within the HSC. Shown here in orange, I have it for point sources, and in blue, I have it for a Sersic exponential profile. And the numbers on the upper right in each panel give you the 95% completeness level. So whereas we had expected to reach to about 24th magnitude, we fall quite a bit shorter because of the, let's say, unpleasant surprise of the overheads that are associated with this. But still, this is deeper than anything that was available until the. And our calibrations seem to make sense. I'm showing here a K-band number counts comparing the measurements that we've got with emirs, which are the black circles with a variety of measurements from the literature. But particular emphasis should be given to the brown points, which are compiled by Scott Tompkins at ASU. I think this is his a Bachelor of Science thesis. I'm not 100% sure of that, but he has done a compilation throughout the whole literature, and it's pretty interesting that we show very good agreement with those data points. Changing gears, now we go to the visible spectroscopy, and the availability of BinoSpec was actually a great boon to this object because it allows observing up to 180 sources simultaneously in a footprint, which is roughly matches the outline of the NEP TDF. A total of 10 masks were observed between June of 2018 and August of 2020, all of which have been reduced using a pipeline developed at the CFA. These observations use the 270 lines per millimeter grading that covers from about 3,900 to 9,200 angstroms with a resolution of 1,340, and a dispersion of 1.3 angstroms per pixel. So this shows you the outline of BinoSpec on the sky, and I also show the objects of one of the masks that we configured. So we can see in red the outline of where the K-band imaging falls. And also shown are the guiding boxes where you put the stars that are going to guide the observations, and as well as the wavefront patrol area, which monitors the focus while the data are being taken. And the background is the I2 image mosaic in the HSC. So as mentioned, there's a custom design software which was made for BinoSpec by the CFA. So the path from raw data to flux and wavelength calibrated is very short. Though when the first observations were taken, the CFA automatic reduction was still in development, and these data were reduced here in Tucson. The measurements of redshift use the custom software that we wrote, and use a combination of data space cross correlation, which is similar to what Sloan uses, and also emission line fits, and all of these were visually validated. So we have a net of over 1,100 actually good quality redshifts in this region, and the spectral resolution is high enough that we can separate the O2 and sulfur 2 doublets and the nitrogen to H alpha triplets, measure some of the physical properties of the galaxies. When creating these observations, selected mainly galaxies, notably VLA, Chandra sources, and Scuba 2 sources. An initial catalog was constructed by combining lists from Rolf's observations using LBC, and an initial catalog from the HSC imaging by Günther Hasinger, which was supplemented by SDSS sources whenever BinoSpec extended beyond the TDF, because this is a smaller region than the current footprint that we have for HSC. And of course, these catalogs have evolved slightly as EMIR's data and HSC catalogs became available, which was done as part of the Pearls collaboration. Here I show the...
Excuse me, you're on the 20-minute now.
Okay, thank you. So this shows us the success rate and also the failure rate for the spectroscopy. So we can see that brighter objects can fail when you have kind of redder colors, which is not surprising, partly because if you have a quiescent galaxy, you need a higher signal to noise to detect spectroscopic features, or also your objects are at high redshift. And of course, surface brightness is a determinant that's not as critical as in the case of fiber spectroscopy. And you can see that this effect even extended as well more compact sources. And of course, really bright sources also get saturated, and we have failed redshifts. But this is something that can be fixed if we use a process similar as that utilized by HSC reductions when they look at really bright standard stars. The redshift distribution that we find in the field from Binospec is shown here, and also showing here the distribution of VLA sources, which was the prime catalog of other sources that was added. And we can see that they pretty much follow the same distribution in redshifts. The quality of the redshift, the spectra can be seen here, and these are sources that match new star. And these are all typically going to be active galaxies, of course, but we can actually see the continuum and really good spectra. And of course, because we have the access to some of the physical parameters of galaxies, we can do diagrams such as the BPT diagram, where I show the Kaufman et al. Pure star formation limits, and also the QLE, the extreme starburst curves. And we can see sources are made within the star forming region, though there are a few in the AGN part, and there are a few AGN sources. There's only one channel source, but I think this is because we probably are being cut off by the redshift limit in such a way that we don't observe the H alpha nitrogen 2 triplet. So the synergies of this are that in spite of having a smaller field, I believe that the near-infrared photometry will be useful for refining photometric redshifts of more distant galaxies within the JNet footprint, since it will extend towards infrared pretty much as Alberto did. And also the availability of nearest spectra on the JWST footprint should allow calibrating these photo Z measurements, since they will provide coverage out to 2.5 microns. The spectroscopy has already been used to calibrate the JNet photo Zs in a work carried out by Antonio, and they should allow an independent assessment of the spectral reconstruction as has been done for the mini JPAS. Both stars have been used to analyze SCUBA 2 sources and new stars data, and are currently being used by one of our collaborators to look at XMM observations. And the near-infrared imaging should enable analysis of the sources that fall off of the JWST footprint, but which have, for instance, HST coverage. So here I will present a summary of the near-infrared imaging. We reach up to 22.3 in wideband and as low as 21.6 AB for H at a 95% completeness level with a 4 exponential profile. We have a solid angle of 230 square arc minutes for YG and K, H and K, and about 313 square minutes for J. The number counts that we measure are consistent with previous measurements. As far as the spectroscopy is concerned, we've got over 1,000 galaxies with good redshifts. The failed redshifts are caused mainly by saturation. Low surface brightness are just because we have galaxy in the redshift desert. And of course, the spectral resolution allows examining some physical parameters of galaxies in addition to measuring the distance. So that's all for me today, and thank you for your attention.
Thank you very much, Chris. I'm taking questions here. The audience. Any questions on the Zoom audience either? I'll ask one in the meantime. Can you, I should be able to get this from the numbers, but can you give an approximate source density for the targets?
Not off the top of my head, but when we designed let's say the spectroscopy, we attempted to have to go deep enough where you'd have a density of sources to the where you could fill in at least a slit. So in way to optimize the slit, it's pretty much the way we did it with Deep 2 when we did that in the EGS and the other fields. As far as the infrared photometry, we don't go very deep, so the density of sources is not that high.
Mhm. You don't have any further questions? Thank you again, Chris.
Thank you.
And we'll try now with Rolf via Luis. Let's see if. Okay.
Thank you. Perfect.
So I guess you will just tell Luis to move as you need the view graphs, right?
That's right. Thank you. Thanks for this opportunity to speak as well. Can you move to the next view graph? So in this talk, I'd like to introduce you or remind you, as the case may be, about what time domain science with JWST entails. What is it and why do we want it? Where JWST could do time domain science. And then I'll talk about this new field that has been developed over the past couple of years, segueing from Christopher's talk, and introduce some of the multi-cycle UV visible imaging that we have taken with Hubble, and the first near-infrared observations with JWST, and what kind of synergies with JPAS there might be. Next slide, please. So, with the advent of the era of deep and large area survey time domain science, it's now possible, or will be possible very soon, to get time domain sequences of very faint objects. For instance, with span stars, or with the Rubin LSST survey, or with the Roman Space Telescope when that launches. And that can be both in our solar system, outer solar system, say. It can be in our galactic neighborhood and beyond, and all the way to very large look-back times at cosmological distances. Next slide, please. Now, what would JWST potentially add? If we look at the Rubin LSST survey, then we see that they will probably get of the order of 23.8 magnitude at 10 sigma for each pair of 15-second exposures, which is one visit. And they will repeat that with a cadence somewhere between 15 minutes and an hour over a very large fraction of the sky. Now, the large fraction of the sky, of course, JWST cannot match, but it can go on similar timescales to magnitudes somewhere between 26.8 and 28.3 magnitudes at 10 sigma, as long as you can find a suitable survey field. Next slide, please. That would be an unexplored magnitude regime for variability studies, any magnitudes fainter than 24 magnitude. And that would open up a very large discovery space for supernovae of various types. For instance, type 1a supernovae would be detectable to a redshift of 5, core collapse supernovae to a redshift of about 1.5, but pair instability supernovae would be essentially visible throughout the universe, no matter how far away they are. You could also do, you could search for the AGN variability, specifically weak AGN variability, which is an alternative way of selecting AGN. That's not necessarily 100% coincident with, say, X-ray surveys or radio surveys. It's also an unexplored regime for proper motion detections. At these limits, and assuming a lifetime of at least 10 years for JWST, you could measure and detect objects that move in the extreme outer solar system, maybe not quite the Oort cloud, but definitely anything incoming beyond the orbit of Neptune. You could search for interstellar asteroids and comets, such like Oumuamua and Borisov. Nearby galactic brown dwarfs and low mass stars would also be visibly moving over such timescales and at these in this regime for proper motion. Next slide, please. So where can JWST do time domain science? Next slide, please. JWST has several operational restrictions, and those restrictions translate into orientation restrictions. So you have sun avoidance, power generation, and shielding requirements that restrict the typical visibility of an object in the sky to 2 time intervals per year. However, in 2 small continuous viewing zones, one in the north and one in the south, centered on almost the north ecliptic pole and almost the south ecliptic pole, you would be able to observe an object or target 365 days per year. And because you can observe it at any time of the year, you can also observe it throughout the year at any orientation that you may desire because of your particular instrument. Like a spectrograph slit can be oriented any way you want. That's not true anywhere else in the sky. Next slide, please. So the date of observation dictates the orientation on the sky, and that limits the range of possible orientations and efficient use of instruments in parallel, except for objects located within these continuous viewing zones. The reason why you would want flexibility there is that it's very efficient if you can rotate your entire focal plane over 180 degrees and match the footprint of one instrument 180 degrees or a half a year later by another instrument. That way you can effectively survey the same area on the sky, or a significant fraction of the same area of the sky, with 2 separate instruments. Next slide, please. So if you want to do time domain science on scales of minutes to years with JWST, then the survey field must be located in these continuous viewing zones. And unfortunately, that means that existing well-established field from HST, Chandra, XMM, VLA, they just don't do. So let's take a look at the near-infrared imagery, foreground extinction, and density of sources that are significantly brighter than the saturation limit of JWST's instruments. Next slide, please. So on the left, in the 2 panels on the left, compare the north ecliptic pole area and the south ecliptic pole area when viewed essentially in a super wide near-infrared filter going from 1 micron to 5 microns. The north ecliptic pole area is significantly cleaner or emptier than the south ecliptic pole area, and that is due to the presence of the Large Magellanic Cloud and some galactic structures. Next slide, please. The same is also true if we look at the middle panels, which show the EB minus V due to galactic foreground dust. The north ecliptic pole area is far cleaner, even though some portions of that area are still affected by galactic cirrus mostly. But there are empty purple areas here that would be suitable. That's not true for the south ecliptic pole area. Next slide, please. In the right 2 panels, I encode the number of sources within a 14 arc-minute diameter area that are brighter than 15.5 magnitudes in K-band. And it turns out that limit is due to the saturation limits, deep saturation limits of NIRCam. But it turns out that very few such regions actually exist. Regions of this size typically have several stars of this brightness or brighter in them. And it turns out that only in the north ecliptic pole area are there areas that large or larger that are relatively clean. In the south ecliptic pole area, none such areas exist. Next slide, please. So there's no solutions for a time domain field with JWST in the south ecliptic pole area unless you want to do time domain science on the Large Magellanic Cloud. The very best region in the North CVC also has guide star solutions for Hubble. It's actually also slightly still in the Hubble CVC. There's a bright quasar in this field that can serve as a phase calibrator for radio interferometric observations. And because it's in the ecliptic poles, it has a low galactic foreground extinction. So it's an low zodiacal foreground emission as well. the poles have the lowest foregrounds. So it's the darkest area of the sky. So that gives us this ideal position that I list the coordinates here for, that are not quite at the North Ecliptic Pole proper, but about 3.5 degrees away from that. Next slide, please. Here's a different view of where in the sky that area is. So we are pointing about 33 degrees away from the galactic midplane and about 96 degrees away from the galactic center. And this is a relatively long but clear sightline through our galaxy. So because that sightline is relatively long, it's also a good field for galactic time domain science. Next slide, please. So the first thing we did after selecting this field and thinking that maybe we got a good time domain field was to verify it using the Large Binocular Telescope and the LBCs. So in UGRIZ imaging, we went to not JWST depths, but significant depths where if there was anything untoward in these fields, we would have detected it. This proved that there were no bright red stars in this field. There was no hint of galactic cirrus or anything that would make this not a good deep field. Christopher Willmer has talked about the near-infrared observations in this field that also started around that time. And third, we got a very deep VLA in VLA 3 gigahertz observations, 10 centimeter, in both the A and B configurations that reached to about 0.9 microgensky near the field center. Next slide, please. So having proven that this is a good field, we were somewhat surprised how eager and how willing the community has responded to this field. Next slide, please. In only 5 years' time, this field has been observed all the way from hard X-rays to very long wavelength radio observations, and with almost any major facility around. This by now is truly one of the best developed deep fields in the sky. It is the deepest new star field, for example, with almost 1.5 megaseconds depth already. It is one of the best deep fields of Chandra too, although it does not reach the 4 megasecond depth of the Chandra Deep Field South. And similarly, several other facilities have spent considerable time developing this. As part of his IDS GTO time, Roger Windhorst has allocated 49 hours of his proprietary time to this field. And in order to leverage that and develop it also with Hubble, we promised to make the first spoke that will be taken with JWST public immediately. That data is public right now. Next slide, please. I should also say that the field was also selected as one of the test fields and one of the exploration fields for a mini JPAS. So there is 56 filter photometry in this field from mini JPAS, and that has already proven quite important. Next, I'll tell a little bit about the multi-cycle UV visible imaging campaign with Hubble. Next slide, please. In cycle 25, we got awarded 36 CVZ orbits, Hubble CVZ orbits, to explore the inner portion of this North Ecliptic Pole time domain field. And we used a strategy where we danced the two cameras, ACS Whitefield camera, Whitefield channel, and Whitefield camera 3 UVIS around the field center. And since this field has 7 opportunities in the CVZ per year, we get configurations that are about 54, 55 degrees apart on the sky. And that means that in six of these configurations, you can trace an annulus, a donut on the sky, and then we filled that central hole with a separate visit that then also produces one flanking field towards the southeast. The depth here is about 10,000, just shy of 10,000 seconds in each of F435W, blue light, and 606W, yellow-green, and then almost 20,000 seconds of integration time in the UV filter F275W. These are filters that are inaccessible to JWST. The depth we reach in these times is quite comparable to what you can get with JWST in about an hour of exposure time. Next slide, please. 2 cycles later, we built on this inner donut or this inner rosette by putting an annulus of observations around that original data set. Now, in 7 opportunities per year, you cannot fill that outer annulus. So this took 2 cycles to do so. And in blue shown here is the final visit, the final hole that's being plugged or that has just been plugged at the end of November. And in pink or purple is the corresponding position of the Wide Field Camera 3 UVIS camera. So here we did not dense the cameras around the center, but we densed them both around in an annulus, sort of one tracing the other or following the other. So that program is now complete. And this was led by myself and by Norman Grogan at STSCI, who designed these patterns. And essentially, we managed to squeeze overall in this program in 96 orbits, we squeezed the equivalent of well over 200 orbits of exposure time, of regular orbits. And we reached depths in 606W of about 29th magnitude at 5 sigma. Next, please. So shown here is a mosaic of what we have, except that one hole that was just recently plugged, that's not yet incorporated into the mosaic. And we show where the designed NIRCam footprints would fall with JWST. The orange large spokes that extend the furthest out correspond to the NIRCam coverage that we desired. And then sort of 2/3 of the way in to the inner dashed circle, that's where NIRCam can overlap NIRS wide field slitless spectroscopy can overlap NIRCam imagery taken either 6 months before or 6 months after. So the GTO program that's taken, that's part of the PEARLS program, consists of 4 of these spokes, orthogonal spokes, that are taken about 91 days apart, and that also corresponds then to 90 degrees, such that we can make that overlap happen. Next slide, please. The quality of the HST images is quite good. It's really only limited by the fact that these cameras have been in space for an awful long time. So the degradation of the actual detectors is significant. So we had to mitigate the CTE, the degradation, by post-flashing these data, and also by taking them at a smart timing within a CVZ orbit, where we essentially let leak a little bit extra of Earthshine onto the detectors when we were observing a UV or a blue filter, whereas the darkest portion of the orbit was reserved for the F606W filter. Next slide, please. And there's more of these details that that really pop out from objects that are intensely blue or ultraviolet bright, all the way to objects that are intensely red. Next slide, please. And there's some more details here in the next slide. So let's move on then to the first near-infrared observations with JWST. Next slide, please. On this mosaic of the HST F606 imagery, I place an outline that sort of points down from the center. That corresponds to the first full spoke that was taken with JWST NIRCam in this field. Now it is not quite as designed. Each spoke consists of a mosaic, of a 2x1 mosaic of pointings. And these 2 pointings in the mosaic do not need to be taken on the same day. We had hoped that they would be, but doesn't need to be. In this case, when the second part of the mosaic was taken, JWST lost its guide star because the guide star turned out to be an unresolved double in the guide star catalog. We were granted a redo of that observation, but the earliest that redo could happen was 14 days after the first part of the observations, first part of the spoke. By that time, the particular orientation of the sky was no longer available to JWST. So there's a 10-degree difference between the 2 parts of this mosaic, and that creates this crook or this hook in the coverage. It does mean that the overlap with NIRIS will not be perfect. We will still have more than 80% overlap, but it's not perfect. Next slide, please.
Rolf, excuse me, it's the 20-minute mark now.
Okay, thank you. Here is shown in slightly shaded blue areas what was actually taken as part of the first spoke and also the second spoke. And then in open wireframe is shown what is still planned and will happen in 2023. Sort of overlapping with those wireframe spokes are other footprints that correspond to NIRIS. In those footprints, we will have wide field slitless spectroscopy centered on 2 microns and in a relatively narrow bandpass to avoid object overlap or mitigate object overlap. Next slide, please. And yesterday, we had a NASA weblog released and a press release from ASU on this first spoke. This first spoke, again, it's the public data. You can download this data from MAST. Very soon we will have a link to the actual mosaics as well. And this is all associated with the first Pearls overview paper that was just appeared online in Astronomical Journal, and that will officially be in the January issue of Astronomical Journal, led by Roger Windhorst. Next slide, please. Since the observed range in wavelength spans everything from 0.25 microns to 5 microns, we had to compress that wavelength range to somewhere within the range the human eye can see. So it's a compressed color, and yet it's a hypercolor image where we sample everything from UV through 5 micron or 4.8 micron. And that creates a rather stunning view of the universe in this little patch of sky with extreme colors showing up quite well. We have objects that are visibly very blue all the way to objects that are essentially detected only in the longest wavelength NIRCam image. One of the striking features is that so many of the galaxies at relatively low redshift, somewhere around 0.3 to 0.6, we see a lot of these brighter galaxies that are detectable in JPAS as well, show streams of stars, evidence of mergers or ongoing assembly. We also see galaxies that were not detected by Hubble at all. They are only detected in the NIRCam filters, and yet they are quite bright in the NIRCam filters. Next slide, please. So what are the synergies with JPAS and JNAP? Next slide. JPAS has the unique capability of providing spectrophotometric redshifts over a wider field. So JWST provides what is effectively a pencil beam survey, very deep, but a pencil beam survey, whereas JPAS can provide a census of the foreground structure. And many JPAS redshifts of this field have already proven helpful to ascertain the likelihood of a galaxy-galaxy lens and the nature of a Seyfert galaxy's radio and X-ray counterparts. Conversely, JWST NIRCam morphological information and NIRIS slitless spectroscopy can provide high spatial resolution anchors to disentangle and interpret lower resolution JPAS resolved and unresolved spectrophotometry of galaxies. It can also be used to train star-galaxy and quasar-galaxy separation and identify AGN through the JWST diffraction spikes. It is quite remarkable that the brighter galaxies with extremely bright and red cores, they all turn out to be AGN of some sort. They have radio detections in general, some have X-ray detections. But this might be an interesting synergy when we can combine data across the wavelength regime and with these different observational characteristics, and probably many, many more. So last slide, please. So I would like to thank you for this opportunity to talk. And if you are interested in moving objects or celestial beacons that vary in brightness, then this field is for you. Thank you very much.
Thank you very much, Rolf, and thank you, Luis, also for your help.
Much appreciated.
Questions here in the live audience? Pepe?
Thank you, Rolf. This is a great talk. I have a curiosity about these galaxies you mentioned that were only detected in the near infrared, but not previously. Are these galaxies a special kind of morphology? Are they irregular? Are they compact red ones?
There is a good question. There is, or there seems to be a range. Some of them I would qualify as nothing but a blob, but some seem to be well organized enough, even though they may be quite small, but they seem to me like they could be an elliptical morphology or a spheroidal morphology. Others might be more like a disky structure. So it's a range of structures. The sizes, like originally everybody would have liked these things to be at extremely high redshift, but the sizes and brightnesses seem to indicate that they could not possibly be at much more than a redshift of 6.
Great.
That's kind of moderate redshift now, yes.
No.
Yeah, well, when I was in grad school, that was absolutely cosmological redshift, but
absolutely. Chris was pointing out in the chat that many of those are also Alman scuba sources, I assume too. It just showed up on the screen. Thank you.
That's right. So they could be extremely dusty of some sort. Whether or not it's the dust that we understand or not, I don't know. But to some extent, the dust must have properties that almost reproduce a break, which is not trivial to do.
Mm-hmm. Yep.
Yeah, I had just a couple of technical questions to clarify. So you said this compressed colors, they go from UV to the NIRCam wavelength. So the UV is coming from the HST, right? So you're packing them together?
That's correct. Yes. So in the color composite I showed, there were 3 HST filters and 8 NIRCam filters combined.
Okay. So the 7 one, sorry, that's okay. It's just a fast question, so just so I understand this. So you mentioned that there was a 15 minutes to an hour cadence. I'm not sure what does this mean, because you mentioned this was possible to do, but I'm not sure that this was done. So is there any cadence in the JWST observations?
In the observations themselves, the GTO observations, there is only the cadence of 180 days, because the NIRIS wide field slitless spectroscopy also has very deep F200W direct imaging, and that filter is fairly well matched to the NIRCam F200W filter. So that will be useful at that cadence. Now within a single spoke, we have the cadence that is dictated by the 2x1 mosaic. There's some area of overlap, even though that is not the full footprint, but it's of the order of about 35% overlap. There we get effectively a second epoch that is separated from the first one by the same amount of time that was between these two observations. In the original design, that could be as short as 5 hours. As it was actually executed, it is more of the order of a day, 23 hours.
This was by chance, not by design.
No, it turns out that JWST is actually quite hard to schedule. And there's lots of pressures on both how long you can observe at a given field and collect data, how much data you can send back down to the ground without losing anything. And all these things conspire in such a way that we were really pushing the limits here.
Okay, thank you.
Yep. See more questions here, and I don't see any questions on the other audience either. So, well, thank you again, Rolf, for your talk. It was very interesting, and thank you, Otto.
You're welcome. Thanks.
Thanks to all the speakers, including Matt, I think already left. And I'm just giving a message to my other people here, Andrea, Josep, Manel. I think we will be starting at 5 o'clock as planned. So you people here have a quick coffee and we'll reconvene in 20 minutes. Thank you.
Thank you. Okay.
Okay. Please take your seats. We're about to restart this final session.
Our next speaker is
Andrea Merloni, who's going to tell us about the early results from the eROSITA survey. And Andrea, please, the field is yours.
Thank you very much. Let me know if you cannot hear me or see my slides well. So
now it's fine. Thank you.
Good. So I'm gonna switch gear a little bit and moving to the X-ray view of the sky. I'm not sure how many X-ray astronomers among you are listening to this, and I guess I've met many of you as recent as last June in Valencia at the ES meeting. So I'll try to give you some more new highlights from the eROSITA survey. Of course, I will try to put this into the context of the wide field surveys and arguing in particular that beyond the classical landmarks of X-ray astronomy following neutron stars and black hole, exotic, energetic, compact objects, X-rays have a particular role in understanding large-scale structure. So you know that most of the baryons are in the warm, hot X-ray emitting phase, even though tenuous and quite faint. And as we know very well, clusters of galaxies which trace the knots of the large-scale structure are very strong X-ray emitters. And in fact, these were one of the main motivations for building eROSITA as a wide field telescope, as opposed to the current, or at least the past workhorses of X-ray astronomy, bigger telescope like Chandra and XMM, which were extremely powerful and have made so much for the field, but were characterized by quite small field of view. And so in terms of X-ray imaging telescope, eROSITA is really the first genuine wide field X-ray telescope. Here you see some very basic hardware characteristic with pictures taken in the integration lab at MPE. The main message of this is that with eROSITA, we have a 1 degree field of view diameter instrument, significantly larger than anything at that same sensitivity before, with a very large collecting area. So at 1 kiloelectron volt, which is kind of a sweet spot for studying soft X-ray emission from clusters, eROSITA 7 telescope that you see here on the left are as large as XMM Newton. They have similar technology for mirror construction, so they have similar image quality of XMM Newton with moderately good PSF of 18 arcsecond alpha energy width on axis, which give you positional accuracy of your sources to about 4 to 5 arcsecond. With very good reduction of stray light, we achieve sensitivity to low surface brightness emission. On the right, you see an image of the CCD cameras. These are also inherited from the XMM Newton technology developments. We have 7 of them with a total of 1 million pixels. These are large pixels of 9 arcsecond in size. But the camera have improved on a number of aspects with respect to XMM, so that we can measure the energy of each photon with an energy resolution of about 80 electron volt at 1.5 keV. So if you don't know, when you take an X-ray image with a CCD, you are essentially doing an integral field spectroscopy, provided you have sufficient number of photons. So the eROSITA was launched on board of Spectrum Röntgen Gamma in July 2019. We spent about 3 months doing calibration and performance verification at the end of 2019. These data have already been released to the public last year, and I will show some highlights from this phase. But the main mission is performing an all-sky survey. And from the orbit around L2, where SRG is located, for geometrical reasons and sky visibility reason, it takes about half a year to survey the entire sky in a continuous scanning mode. So we complete the first all-sky survey in June 2020, and up to the end of last year, we had completed 4 of them. And the plan was and still is, in fact, to continue the survey until we have 8 complete scans of the sky, followed possibly, at least in the original plan, by a phase of pointed observation. As you probably know, we put eROSITA in safe mode, suspending our science operation following the start of the war in Ukraine in February. And so at the moment, we are working with the data of 4 all-sky survey. We are working towards the first data release of the first all-sky survey that will be released to the world next year. And we are still figuring out under which circumstances, if and when we can start science operation. And we hope to be able to do it as soon as possible, of course. But okay, the outline of my presentation, of course, relies on the data that we have received so far, and will be more or less split in 2 parts. Here you see actually a beautiful image in false color taken from the first eROSITA all-sky survey of the hemisphere, of which the German consortium have data access. Here is an RGB image of X-ray photon from 0.3 to 2.3 kilo electron volt, which is the sensitive energy range of eROSITA. EFETS is 140 square degree equatorial. So this image is in galactic coordinates, but EFETS is an equatorial field, which we picked as a demonstrator field during our performance verification. And we observed it with eROSITA down to the depth expected at the end of the all-sky survey. So in just 4 days, less than 1% of the data we have, we could do a lot of verification of our survey machinery in terms of understanding the population of the X-ray sources. And here I will show you 2 highlights relating to large-scale structure and AGN. And then in the second part of my talk, I will go over highlights from the all-sky survey. So let me start with EFETS. This is, again, an X-ray image of the field, 140 square degrees, split in these 4 rectangles. It's a kind of observation that no other X-ray telescope has done before, in the sense that we observe 140 square degree with a 1 degree field of view, not doing pointed stare, that would be quite inefficient, but rather doing raster scan observation. So moving the telescope back and forth continuously. And we expose only about 2.5 kiloseconds, so it's less than 1 hour average exposure in any point of this field. Still, because of the large sensitivity, we detect more than almost 30,000 X-ray sources, which makes the EFETS field the largest existing X-ray contiguous X-ray survey apart from the all-sky surveys. Of course, we chose this field not by chance as a field with a very good multi-wavelength data. There is hyper-SupremeCam wide survey data. There is SDSS, Viking, and we have targeted, and gamma, there is one of the gamma 9 field. And we have targeted ourselves with SDSS 4 and 5 spectroscopically, so that now we have accumulated at least 12,000 good spectra of X-ray sources, X-ray AGN and stars, plus similar number of galaxies that are within clusters detected in the field. So it's a very rich field. The data are public, and so there is quite a lot of science coming out of it already now. So of course, one of the first things we did is to verify our source detection and identification process. This image is a color optical mid-infrared color using GRZ and WISE-W1 of the point sources in this field, of these 27,000 sources that we detect in the field. And this is a nice parameter space for the sources. These are the sources that makes most of the X-ray background. So it's kind of the average run-of-the-mill X-ray survey you will find in a random field at the depth of eROSITA. In this color space, you can separate quite well extragalactic sources. Here are color-coded in blue from galactic sources in red. And here we use everything we can from spectroscopy, astrometry, from Gaia, and color themselves to classify the sources. So what you see in the blue cloud, there are mostly quasar on the left, or elliptical galaxy. This is the track on the right. And here is, of course, star main sequence, M dwarf, and so on. Plus, quite a lot of red sources in the quasar space, which are CV, cataclysmic variables, and white dwarfs. So the identification process, even with our relatively poor or not Chandra-like PSF, is well under control. This is maybe interesting for this audience, is a plot of the R-band magnitude versus flux for the sources we detected in the IFETS field. Black are our extragalactic population and red are our galactic population. So they split quite well in the optical to X-ray plane. This is quite well known from X-ray astronomy in the past. Here I'm putting with the dashed line the expected X-ray flux optical magnitude range. We will follow up with spectroscopic facilities. We have teamed up with STSS-5 and Foremost, and we expect over the next 5 to 10 years to reach more than 1 million optical spectra of X-ray selected sources, mostly AGN, of course, down to this flux limit that you see here. But this image also shows that there is a significant fraction of sources which are fainter than the limit you can achieve with the 4-meter telescope, for which something like JPAS will be a fantastic machine to have more accurate photometric redshift than we can have with existing broadband imaging. Okay, this is now a result which is coming out soon, so it's almost ready for submission, led by Joan Comparade MP, where we have take advantage of the existence of very large galaxy spectroscopic samples, thanks to Gamma and STSS, to place the X-ray selected AGN onto the large-scale structure, basically doing a clustering analysis. Here you see a nice cone. This is not simulation. These are real data that show the Gamma galaxy in the field in gray, the location of the X-ray selected AGN with the blue crosses that you actually see with your own eyes following the large-scale structure. And in red, you see the clusters we detect in IFETS with eROSITA that I'm not going to discuss in this particular part of my presentation. So here, what we have done is taken advantage of this spectroscopy, but also on the very good imaging quality of HSC. We have done at the same time lensing and clustering on the X-ray selected AGN up to redshift about 0.5. We are targeting sources with an average X-ray luminosity of about 10 to the 43. So it's not as deep as, you know, the Chandra deep fields, but you are probing sufficiently well beneath the knee of the X-ray luminosity function. So these are interesting population, which are the bulk of the X-ray emitting AGN at this redshift. So the combination of clustering and lensing allow us to constrain with unprecedented detail, in fact, the HOD model of the AGN population. Here you see on the right in gray our measurements and the split between centrals and satellites, and in yellow a possible modeling of that using semi-empirical models like the one that Joan Comparade put together a few years back. And so here, yeah, you see some measurement of the average halo mass, the width of the one halotherm distribution, and the slope of the satellite fraction. So these are all improvement on previous X-ray selected AGN constraint, including something I'm not showing here, but a potential dependence on clustering on X-ray luminosity. But you can imagine that if you extend this work from 140 square degree to the whole sky, in the future there will be fantastic clustering analysis that you could do, splitting your population according to different properties of your AGN. For example, obscuration, radio property, and so on. And here actually is a comparison between past model of the AGN HOD from the literature. So you can start testing modeling models of, for example, AGN activation in satellites versus central in this data. Okay, that was kind of a sneak preview based on this 1% of the data. The bulk of our result, of course, come from the Whole Sky Survey. And here I'm going to focus on 4 different topics, keeping within the extragalactic science, hoping this will be of interest for some of you. Well, okay, this is just an hemisphere view of the Whole Sky Survey. This is now a full sky view of the eROSITA sky, but now you see here we are only picking up one of the 3 RGB bands we've used for this color image. This is the energy range between 0.6 and 1 keV. This is a 8 of projection in galactic coordinates, so galactic center is at the center of the image, the galactic plane is horizontal. And this is an interesting energy range because in this energy range, most of the high galactic latitude sky is dominated by the cosmic X-ray background. So mostly this cosmologically distant AGN. In fact, you see it's quite uniform, but the hottest phase of the Milky Way CGM emit so gas of a few million up to 10 million degrees, thermal gas in this range would emit in this band. And this is where we made probably our first major discovery, which mainly is the presence of this figure of 8 like bubbles tracing the hot gas from symmetric towards the galactic center. The north bubble, so to speak, was well known as North Polar Spur, and in fact is still under debate whether it's all whether there is some other sources in projection, but we have discovered for the first time a southern component associated to that. This is the same image in cyan, overlaid in red with the Fermi hard image above 1 gigaelectron volt. And here you see the famous Fermi bubbles coming out from the galactic center. And the eROSITA bubble, so what we call the eROSITA bubble, seems to very nicely enclose these Fermi bubbles. We are now working on doing detailed spectroscopy of the emission from this bubble region using this spectroscopic capability I mentioned to you. In our discovery paper that's already 2 years old, in fact, almost exactly 2 years old in December, we put together a simplified kind of a toy model based on spectroscopic observation of skewers, a line of sight with XMM newtons that give us an idea of the temperature inside and outside of the bubble that allow us to estimate a Mach number, therefore a total energetics, about 10 to the 56 ergs, and an age, which is quite uncertain, but it's ranged from a few million up to a few tens of million a year, and therefore an energy release rate needed to inflate these bubbles between 1 and 3 10 to the 41 ergs per second, which is relatively easy to do for a weak AGN that could have been ignited in the past. And after our publication, interestingly enough, people that do numerical simulation of the hot CGM and the interaction between AGN feedback processes and the CGM have claimed that this kind of bubble, relatively weak and visible only nearby objects so far, should be quite ubiquitous. This on the right is actually a picture gallery from a paper led by the Lucis DMG simulation, in which they claim that thermal-like AGN feedback at not excessive power, but for a Seyfert-like episode of emission should be traced by outgoing shock and bubble-like emission in the tenuous X-ray atmosphere that we can see with the eROSITA and the Milky Way. So I think there is quite a lot of interest now, well, in the broader community about how the hot gas reveal the process of AGN feedback and galaxy formation, and this circulation of baryons in the CGM. There are plenty of open questions in this field, starting from the baryon and metal budget to the exact role of AGN feedback. And it turns out that even if we can only detect so far CGM of Milky Way-like galaxy within our own Milky Way, eROSITA is a perfect instrument given its wide field and excellent sensitivity at soft X-rays to say, at least on a statistical sense, something about this population. So there is ongoing work trying to study statistically CGM by stacking the X-ray emission from eROSITA in large number of nearby galaxies. And I think this is also something that could be of interest looking in the future as a synergy between eROSITA and JPAS. So the work right now that I'm describing here follows a paper we published last year, or this year, by Comparat looking at effects, but now we are going after the Old Sky survey data. We are using legacy DR9 galaxy sample with photometric redshift and targeting galaxies in this very narrow redshift range between 0.03 and 0.1. And here, of course, having better photometric redshift will be of tremendous help. And we are then stacking the X-ray events at the location of this sample of hundreds of thousands of galaxies. Here, it's just a test we are doing to verify the completeness of our galaxy sample. Of course, we are quite well complete at high masses, and we are focusing our work on masses around the Milky Way between a few times 10 to the 10 up to 10 to the 11. Here you see the result of this experiment. Here we are looking at the stack of blue galaxies with a mass around that of the Milky Way, I think around 10 to the 10.7 solar masses. We clearly detect a signal. So you see here, the green is the background. There is no doubt that there is many sigma detection of X-ray, soft X-ray emission associated with these galaxies. We have, of course, removed all the non-AGN. But this signal is very compact. Here in gray, you see the convolved PSF from eROSITA, which of course is not excellent. So here it's probably, we cannot claim with any significance that this emission is extended beyond the PSF. This is a background subtracted profile. And this is, I don't know if you see it very well, but there are 3 different profiles, background subtracted profiles from 3 different mass ranges, from 10 to the 10.1 to 10 to the 10.8, that you see an increase as expected. You see brighter emission from more massive galaxies. The situation is quite different if you look at red galaxies. There is a very strong extended signal extending up to a megaparsec when you do the stack. Here you see the background subtracted signal. There is really a very strong signal here. But of course, one has to be careful, okay? Because we are stacking everything in projection. So, for example, if, as we think we know, red galaxies prefer to live in denser environment, the emission from the hot CGM of this denser environment will be included in this stack. So as an experiment, what Yi Zhang, a student at MP who is leading this paper, has done is taken, this is a portion of a piece of the sky in the legacy survey. All these circles trace the galaxy, and the size of this circle is proportional to their virial radius. And here you see a lot of overlaps, right? You see a lot of systems that are overlapping with each other. And so what we have done is to define an isolated subsample of the galaxy in which we excluded all galaxies which have a significant overlap with nearby neighbors, at least in projection, right? And the solid lines are this that you see here is this isolated sample. This isolated sample removes a lot of red sequence galaxy, which is another indication that red galaxies tend to live in denser environment, and leave most of the blue cloud galaxy there. So when you do then compare the stack of the isolated versus the non-isolated sample, here you see for the blue galaxies, there is not much of a difference. Here you see the different level of background just because the stacking area are different, but the background subtracted profile here on the left are essentially identical. And we detect the same signal up to about 100 kiloparsec. While if you look at the red, The dark red are the one I showed you before, but then if you look at the red isolated galaxy, the signal is much more compact. In fact, most of this emission between 100 and 1,000 kiloparsec has a profile that is reminiscent of these two halo terms. So we are actually seeing in projection the effect of the environment this galaxy live in. So what we need to do next is to actually model the entire profile and the clustering properties of these galaxies. But with the data that we have, we think we can have a go and testing this environment as a function of stellar mass, for example.
Andrea, excuse me.
Yes.
Let's pass the 20 minutes.
Yes, okay. So I'll then move in my last 2 or 3 minutes to two more topics. One is the search for high redshift quasars. This is the compilation of known high redshift quasars up to a few months ago. Only 10% of them are X-ray detected. And in fact, all of them until before eROSITA were the X-ray observation were taken as follow-up from optical discovery. It's quite important, however, to have an idea of the purely X-ray selected angle in looking at high redshift quasar, because of course, we want to understand whether this high redshift population that we have discovered in the optical is biased, for example, towards or against obscured objects. And so in this plot, you see with the red circles, the first 5 X-ray selected high redshift quasar. They all come from eROSITA, from both the German and the Russian team. And the record holder is a quasar that we detect in the EFETS field. It's, in fact, I think all of these quasars were already known in the optical, but now we are detecting them blindly, right? So we are not pointing the telescope at them, we are just finding them in our catalogs. So we can build, for example, a sample that tells us the history of accretion. Here is the accretion rate evolution as a function of redshift. And so because we know the selection function of our survey very accurately, we can turn this few detection into a volumetric rate. And so this is a constraint on the density of accretion from X-ray selected AGN at the bright end of the luminosity function at redshift 6, which seems to confirm this sharp exponential cutoff. And we have we have discovered a few new sources using a dedicated pipeline led by Julian Wolf, a student at MPE, who has selected quasar with a machine learning method, finding the eROSITA association. And until now, we have discovered, we have observed 9 objects, and 5 of them turn out to be redshift 6 quasar with X-ray counterparts. So I think it's going to be interesting. The numbers are not huge, at least yet, in the eROSITA data we have so far. But this, as I said, provide an interesting angle to the high redshift population. And my last topic, of course, is clusters of galaxy, because this, as you can imagine, is the main driver of our cosmological investigation. This is a map of the German eROSITA hemisphere on the right, with these bluish points representing about 13,000 cluster confirmed that we detected as extended sources in X-rays, and then we have used photometric redshift to confirm their nature. So we use everything we have in the Southern Hemisphere, mainly from the legacy, from DECAM, KITS, PanStar, to measure photometric redshift of these clusters. And we have detecting object up, and this is based on, sorry, I should have mentioned, only on the first whole sky survey of eROSITA, the first 6 months worth of data that we'll be releasing next year. And we detect clusters up to redshift 1.1, 1.2. We have even a redshift 1.5 cluster, which is confirmed with an SZ object. And here, just to give you an idea, is the X-ray luminosity versus redshift distribution of our cluster. So of course, a lot of interesting low redshift groups, which is another interesting domain, but quite complete high redshift population for the brightest and more massive cluster. And here, if you just use a very simple X-ray to mass scaling relation, that you shouldn't probably do, but just to give you an idea of the mass range you are probing with these 12,000 clusters, that's the mass versus redshift distribution. And most of our activity right now is modeling our selection very accurately. We have this nice paper led by Seppi et al. That you find on the archive, in which we have created a digital twin simulating the eROSITA sky survey in all detail, including all the cluster AGN, star, background, bubbles, and so on. And we are then running our source detection process on the simulated data in order to constrain our selection function very accurately. Okay, this leads to my conclusion. I will hurry up. eROSITA has been in operation for more than 2 years, and we have completed about 4.4 sky survey, even though since February we are in safe mode, and we have at the moment no clear prediction if and when we can resume our operation, but the instrument is healthy. Thanks to its large grasp and stable background and the observing strategy, eROSITA is opening up a lot of new parameter space for X-ray astronomy across different source classes. Unfortunately, today I didn't have time to go over galactic astronomical sources, which is also an interesting subject in itself. And I'm sure that the Old Sky Survey will represent a unique legacy data set that will be unsurpassed for many years. So there is a lot of synergy to be explored for wide area surveys over the next decade. And you should stay tuned for our first data release that is planned for April next year. Thank you very much.
Thank you, Andrea. It was very interesting, and I'm sure we have questions around here. But at least I do have one for sure. When you showed the spectroscopic follow-up that you plan to do with LAMOST and SDSS?
Foremost, yes.
The limits that you showed, actually, you will cover all the objects down to that limit, or there is a selection function, or?
Yes. So for Sloan 5, we have already started. And here we are going for the bright population, both in X-ray and the optical. So here is this blue square. So we are going for the brighter X-ray sources down to 21.5. But of course, there is also a bright limit. So between 16 and 17, we are not going to cover anything brighter than that for crosstalk reason. For Foremost, I'm not sure whether we are going to put any X-ray flux limit, but for sure we know that Foremost is still a 4-meter telescope. So we can definitely go deeper than Sloan, but not much deeper than 22.5. We are still uncertain how much deeper between 22.5 and 22.8 we can go. That's the current plan.
My question is that 1 million objects that you have in parentheses actually covers all the objects to the limit that you plan?
Yes. We have already submitted the preliminary catalog, even based on this 4 sky survey that we have, that contains in our half of the sky about 1.2 million sources down to 22.8.
Okay.
Point sources, these are only point sources. Plus, I think it's about 50,000 clusters, members, of course, with the slightly brighter magnitude cut for Foremost.
Renato?
Hi, Andrea Renato here. Great talk. Just had one question. So the purity that you mentioned there is about 50% for the clusters. Yes. And I'm assuming that most of the hit comes from this less than 0.2, redshift 0.2, 10 to the 13 niche.
Yes. Well, yeah. So the way I understand this is that we went for a very complete sample. So this number of extended sources, here is the parameter in our, we are doing a beta model fitting of sources with, between 20 and 50 counts. And we are going down to very low significance. So you can take it, this is like a 2-3 sigma extended source, and there are that many. If you were to take a purer sample, for example, cutting X like bigger than 10, which will be like a 5 sigma, then we would have a much cleaner sample, of course, much smaller. So the strategy of the group is to start with a high complete sample with almost 50% contamination, and then use the optical, essentially it's a red mapper optical to clean it up. And that's how we get this 12,000. So you see, it's about half of this extended sample we start from that is confirmed using the red mapper.
So one curiosity that I had is that you mentioned, I think you mentioned that there was some study being done with respect to the metallicity of the Fermi bubbles. Well, the gas around it.
Yes. I mean, I don't have a plot for the semi-bubble, but I have this plot. It's a paper out from Ponti et al., which is looking at the diffuse emission in EFETs. So just very quickly, if you remember, EFETs is out very well on almost at the opposite end of the bubbles, right? The bubbles are here, EFETs is on the other side. So this is kind of a view of the metallicity of the CGM outside of the bubble. Of course, we can do the same inside of the bubble. It's much more complex because there are many components, but the data are fantastic. So in 120 square degree, you stack all your photons and you have millions of them, and you can detect very well oxygen 7 and oxygen 8. So the line ratio gives a very sensitive temperature measurement of the CGM, and then the continuum to line ratio gives you a metallicity. And so we are including all possible systematics we can think of, for example, the presence of solar wind charge exchange and the difference in the cosmic X-ray background slope at low energy. We think we never get more than 0.07 solar for the diffuse CGM in EFETs, with a temperature which is bang on the virial temperature of the Milky Way, between 0.15 and 0.17 kiloelectron volt. So we think we can do this kind of study over thousands of line of sight with the eROSITA data, and that's what we are trying to do right now. But you can imagine it's quite a lot of work.
So was there any kind of gradient measured?
That's what we are looking at. I mean, in EFETs, no. In EFET, we didn't find any gradient. Oh, there is a slight gradient, but we think it's due to foreground NH. But that's exactly what we are doing. I don't have the slides here, but we are putting different 10 square degree line of sight at a given galactic longitude as a function of latitude to see this. I don't have the results yet, but this is what we are trying to do before the data release of next year.
Thank you.
We have time for
One quick question, Alessandro.
I would answer two questions.
Two quickest questions.
So, quick question number one is, since the satellite is in safe mode, is it using any fuel, whatever? Is it consuming something so that restarting the mission could be could result in a shorter mission? And the second question is, the data release is going to be whole sky or just a German part?
Yes, data release next year is only German part, half sky. And I mean, I should have clarified, eROSITA is in safe mode, but the Spectrum Röntgen Gamma satellite is continuing its operations. So it's continuing consuming fuel to stay on the orbit. However, because we don't have any cryogenic consumable, the fuel available on the spacecraft should supposedly sufficient to keep it on the L2 orbit for 15 years. So yes, we have lost 1 year worth of consumables, but this is not the factor.
Okay. Thank you again, Andrea.
Thank you.
We will move to the next talk by Josep Manel Carrasco. He's going to tell us about synergies between Gaia and Javalambre J things. So, yeah. Perfect, Josep Manel. I'll tell you when
you can hear me, I guess.
Yep.
Can you hear me?
Yes.
Okay, thank you. First of all, thank you for inviting me to give this talk about the synergies between Gaia and Javalambre things, as you say. Unfortunately, I cannot be there with you to discuss many details observing, so I'm away and I have to do this talk remotely. This talk is about the interaction between the Gaia data and JPLAS and JPAS data. I know that you are well aware that in combination, both surveys are stronger. So there are, in the JPLAS collaboration, there are 23 projects using Gaia information to develop better science for JPLAS. 14 of them have been already published using the Gaia parallaxes, the Gaia photometry in combination with the JPLAS data to get better determination of the astrophysical parameters or many interesting things that could be done. No? So you are aware that Gaia is helpful for you, and the other way around, JPAS and JPLAS can be helpful for Gaia. For those that are not so aware, I do a slight introduction about the Gaia mission. The main purpose of the Gaia mission, Gaia is an astrometric mission, mainly able to determine the positions of the sources in the sky very accurately with the micro-arc-second level. And as it has several years observing the sky, it can even determine the motion of the stars, determine the proper motion, and also the parallactic effect, providing the distances to the sources. The third motion in the radial direction is provided by the high resolution spectra in the calcium triplet that provides the radial velocity. And we also have some spectrophotometry, low resolution spectra, to get the colors of the sources. These colors are needed for the chromatic correction, for the astrometric measurements, but also to know what are the source that we are observing. The color provides you clues about the temperature, the abundance of the source, and the metallicity, the age, the mass, and so on. So to fully characterize the source that we are observing, not only the position in the space, the motion, and the astrophysical parameters, this instrument built with 100 CCD detectors, surveying the sky, spinning the sky and observing the full sky, while the sources are transiting the field of view. Then we get in these first CCDs, the astrometric measurements. Then we provide the spectra in low resolution in blue and red for the astrophysical parameters, and high resolution for the radial velocity. This same year, we delivered the third publication of data with 1.8 billion sources. Not only stars, but also galaxies, quasar and asteroids. Gaia is observing everything bright enough to be detected and point-like sources. So everything, even galaxies and quasar, everything outside our galaxy or in our solar system are also detected and obtained. We are delivering for the first time the spectra, 200 million spectra with low resolution, and 6 million astrophysical parameters derived from the high resolution spectroscopy, and 33 million radial velocities. So we are building up the size of the catalog in every release. And not only in size, but also in performance, in precision. Here you have how the performance of the parallax and the proper motion has evolved since the first Gaia data release to the second and the third. This one is the current one, and the future expectations for the fourth and fifth data release. But now we are at the level of a few tens of micro-arc seconds for parallax and micro-arc seconds per year in proper motion model. So we are a good quality data in astrometry and the motion of the stars. And also in the third component, in the radial direction, I mentioned before the 30 million sources with radial velocities delivered in DR3. This is the distribution in the sky, corresponding to where the most of the sources are. But here we have it in the galaxy. Here, the center of the galaxy, and this is the position of the sun. So you see that in different directions, we have more coverage of these radial velocities. And with the measurement of the radial velocities, we can analyze the rotation of the galaxies and the motion of the moving groups and local group galaxies and so on. So again, we are providing more science and with better precision also. The precision in the radial velocities is about 0.2 kilometers per second. This depends on the temperature of the source, of course. We are measuring in the calcium triplet, so it's more sensitive to the given spectral types than others. But we are providing good quality for these radial velocities. with this motion, the proper motions, the distances, we can begin to analyze the motion of the stars, and going back into the past, learning what have been the evolution of the galaxy, of the Milky Way in the past, and detecting, for instance, in this case, that in the past 300 to 900 million years ago, the passage of the Sagittarius dwarf galaxy imprinted some motion in the stars in the Milky Way, in the disk, and now we have this feature perfectly seen in the Gaia data. So also the photometry is something that provides a lot of information in the Gaia mission. We are at the level of milliards seconds. We have the white light passband, the G magnitudes, and also the passband integrated in the low resolution spectrophotometry in the blue and in the red range, also at the level of millimagnitudes for PP in blue and RP in red. And for the first time, I was saying before that we are delivering the spectra, 200 million sources. We are almost complete until magnitude 17.6, if they have enough number of transits. And for the faint 10, we have incorporated professor sources, some 100,000 quasars, 17,000 galaxies, ultra-cool dwarf, white dwarfs, and so on, that were delivered on purpose, even if they are fainter than the limit that we imposed for the release. This is the distribution of sources with the low resolution spectra, the spectrophotometry in Gaia, and you see that there are some imprints of the Gaia coverage because these regions have lower number of transits, and this will disappear when the data, more data comes in DR4. So we will be releasing without gaps the coverage of the sky of these low resolution spectra. What is the quality of the low resolution spectra? This depends on the wavelength, of course, and on the color of the source. Different sources with different colors have different shape, providing different signal to noise ratio. Here, it's a source with a given color, but different magnitudes, of course. It scales the signal to noise ratio. And here you have the signal to noise ratio in color index in the color magnitude diagram in VP and in RP. As you have seen, the low resolution spectra is able to see the imprint of the physical parameters. We know that, and this was the purpose to include these low resolution spectra. The temperature makes the spectra look slightly different, and the absorption, interstellar absorption also. We are deriving the astrophysical parameters and providing them to the catalog also. I did an exercise cross-matching the Gaia DR3 data with mini JPAS, the one available for JPAS, at least to me, and then cross-matching the data. The first feature that we see is the color, the magnitude color diagram. JPAS is going deeper than Gaia at this stage. It goes deeper in magnitude, so JPAS is observing more sources than Gaia, and this is a good thing that in combination with Gaia could help to enhance the science that Gaia can provide. Gaia, besides, can only provide data for point-like sources, as I commented before. So JPAS have more variety of sources also. Well, different colors here show the availability of the Gaia data, the Gaia spectra, low resolution, or the radial velocity. And as you have the parallax, you can build the HR diagram of these sources. Now we have few sources, but with the full catalog of JPAS, this can look prettier. Then as JPAS goes deeper, it's a good option to go deeper in the halo structure with JPAS. And this could be an ability that JPAS can provide to Gaia to complement the Gaia data to detect more over densities of these streams and the halo structure of the Milky Way. So this could be a good thing to take into account. The astrophysical parameters that I was commenting for the sources in common with JPAS, these are the parameters provided by Gaia. This could be compared with the estimations done by JPAS as a kind of cross-reference and a double check that both missions are doing it well. As the JPAS goes deeper, an interesting thing could be to use it for going deeper in the extinction regions. And also besides, JPAS is more sensitive in the ultraviolet than Gaia is. And these ultraviolet measurements can provide a better extinction determination. So the combination of both surveys, again, it's a good thing to do. I will not enter into much details. The stellar parameters, we know that with J+, with some color diagrams, we can determine the astrophysical parameters. We have seen this week that you are quite good determining the astrophysical parameters. So the information of both data with in combination with Gaia can be very helpful. If we compare the resolution of JPAS with respect to the Gaia low resolution spectra, BP and RP, the resolution of BP and RP is depending on the wavelength, and sometimes Gaia is better than JPAS, sometimes is worse in resolution. But take into account that the spectra in Gaia have the PSF blurring the wavelength information. This is one thing that JPAS doesn't have. The passbands, the filters, are not allowing wavelengths outside a given range entering into the measurement, and then you have cleaner information with similar resolution. You see here the comparison of the Gaia pixels in gray with the JPAS passbands. In resolution, sometimes, as I was saying, Gaia is narrower, sometimes it's wider, but the information is cleaner for JPAS. And this is something in the determination of the metallicity that can be very helpful. And then we should exploit this to determine the metallicity, the chemical abundances, because it's very interesting. And we know that, for instance, the determination of H's that fitting some isochrons depends on the metallicity. A good an accurate determination of the abundance is very helpful in this sense. And also the determination of ultrametal pure stars. There are very few halo stars, very rare, with extreme low metallicity. The determination of the metallicity can complement very well the Gaia data that can provide the astrometric data, for instance, the proper motions and so on. And also, this can help in the determination of the history of the Milky Way. For instance, we know that the Gaia Enceladus 10 gigayears ago was trapped in the Milky Way, and this can be determined with a good metallicity characterization. As I was saying, the interaction between Gaia and Javalambre team has been very active. We inside Gaia participated in this paper, for which we built some synthetic photometry from the Gaia low resolution spectra, and we take care that the JPAS and J+ filter systems were included in the tool that it's able to provide this synthetic photometry for the community, Gaia XPy. And this is the tool that Carlinhos mentioned on Tuesday. But it's helpful also for us to see the quality of our data. How are we doing with this first delivery of Gaia data in the spectra? And we can see, comparing the catalog data with the synthetic ones, that we have a 0 point, and that we have some issues in the ultraviolet that need to be improved in future releases for Gaia. We can determine also, in this case, without using JPAS data, only synthesizing the JPAS passbands in Gaia. It's a very interesting system to synthesize because it covers all the range in Gaia, and we can see the quality of the spectra in different ranges. And we see that there are some features in BP different than in RP, and also in the ultraviolet, as mentioned before, that we have some limitations nowadays in the data. This is the one slide from the presentation by Carlinhos on Tuesday, that we are happy that this synthetic photometry from Gaia spectra, even in the ultraviolet, is helpful to increase the quality of J+ calibration. So again, in the combination of both missions and comparing the standards that we use for Gaia, as Carlinhos did, to determine the absolute value of this comparison of the two systems and the Gaia and the J+ calibration. Dealing with white dwarfs, Gaia is able to derive good HR diagrams, splitting the white dwarfs in helium and hydrogen type white dwarfs. With the synthetic photometry approach, we used J+ and JPAS filters to see how well we are able to discriminate with a random forest algorithm between these two types of white dwarfs, DAs and non-DAs. And you see that JPAS, it's performing good because it covers all the wavelength range with a lot of filters, so provides a lot of information with less confusion. Although the use of all the coefficients in the Gaia spectra is better because we are reducing somehow the information that we have by synthesizing some spectra from this spectra, from the Gaia spectra. Okay, until now I have talked about the Milky Way. Maybe if you are more interested in the extragalactic information, you are bored now. But Gaia is observing not only data from the Milky Way, but from other sources, and also the evolution of the galaxies that you use in the external galaxies need to be tested in the information we have in the Milky Way, and the other way around. The information from the Milky Way is able to build better models. So a collaboration between these two fields is needed, and it's being done. Here, for instance, you see how the individual stars in the Large Magellanic Cloud, the proper motion determined by Gaia is able to provide the motion of the stars around the center of the galaxy and get the rotation of the Large Magellanic Cloud. But as I said, Gaia observes not only stars, but galaxies and quasars. We have delivered these 3 million and 2 million of these types of sources. Cross-matching with mini JPAS. In Gaia, we provide a probability of being a quasar and a galaxy, and we have few tens of them having been classified as quasars and galaxies in Gaia. Most of them are stars, and some are variable sources. But this parameter could help you also in the determination of the discrimination between quasars, galaxies, and stars.
20 minutes,
Okay.
Josep.
20 minutes, thank you. Then, using these systems in combination with the galaxy could help in training the algorithms, as I say, the classification of the sources, to analyze the stellar content of the galaxies in the local group, and the redshift calibration. For instance, with the BP and RP spectra in Gaia, we are able to get the spectra as it was seen in a rest frame for all the quasars in this paper, and taking away the redshift effect and putting all the spectra of different quasars in the same level, we can build normalize mean spectra for the quasars and determining the redshift for the different quasars. And then we build a mean composite quasar spectra that could be helpful in some studies. This is not ending here. Gaia will provide more data before Gaia data release 4 at the end of 2025. We will provide some focus releases with this content. You can see more information in this webpage with the planning of the releases. For the last release, we will publish everything in the nominal mission, also the epoch data, which will be very helpful, and the mean spectra and mean data for all the sources for the nominal mission. Gaia DR5 will go for the extension mission. Then, in summary, I will start to finish. The information that Gaia can provide to JPAS, Gaia provides a very good astrometry, photometry, and kinematics, parallaxes that can build better HR diagrams in JPAS and JPLAS. The better resolution, it's a space-based mission, so the better resolution can help discriminating between contaminants in the catalog of JPLAS. The use of the standards used for Gaia can help in the calibration of JPLAS. This is being done also. The synthetic photometry library, the astrophysical determination, and the other way around. JPAS can help to Gaia because JPAS goes fainter, goes deeper in distance, provide better ultraviolet signal, and it's helpful for determining the astrophysical parameters, the abundances. And well, there are some participation marginal that can happen to help determining the astrophysical parameters from JPAS. And in combination with SLOAM, for instance, determining the proper motions for those sources not accessible for them. Then a lot of science can be derived through this. And maybe I am starting to finish here. So thank you very much. And if you have questions, I can answer. Thank you.
Thank you very much.
Questions around here?
Okay, we have, no, that's clapping. That's another thing.
Thank you.
Here. I assume the stellar people would be just jump.
We've been jumping on that for some time.
So you know everything already.
I'm actually organizing a meeting to sit down with Josep, Karma, and others in Barcelona.
Sure, we are doing some teleconferences when needed with Carlinhos very often. So if you are interested in arranging some of these, it's nice. It's a pity that I am not there to discuss the details with you now, so, but we can arrange something.
But
please,
since everybody else is shy, can you comment on the since I'm the PESAL on the M31, can you comment on the Andromeda dataset?
Yeah, it has been released, some region around Andromeda, including the epoch data. So we are not releasing epoch data these days, well, in DR3 generally, but for this specific region, we know that Andromeda galaxy is quite interesting for the determination of the distance with Cepheids and so on. So we provided the data, and there is a paper in the Gaia collaboration dealing with that. So you have more information there, and the data is also accessible now, so you can download it without problems.
Well, everybody keeps being shy. So thank you very, very much again, Josep, Manel, to all the speakers of the afternoon. And I can now officially declare the session closed. And now there is a session about final remarks by, I guess, some of our beloved leaders.
I'll be brief. So what would you with the projection? I changed the colors a little bit to be a little bit more optimistic. It was too dark. Okay, so just a few words. Well, it was actually very nice. That's, I think, my first meeting since the initial beginning of this pandemic. It's very nice to see you in 3D. So just a few words of what I remember. If there's something else that you like to highlight. Sylvia, I think she's on the road now. She cannot, maybe she cannot participate directly.
She's online.
Yeah, but on the road, whatever. Okay.
I'm here. I managed.
Oh.
Hello.
Welcome. So if I forgot something, please add. So in general, I can say that the winds are on our side this time. I mean, I think I've been here a few times now. We are about to begin, but it seems that we're about to begin the scale weeks. So that's pretty good. So JPAS is transitioning to pure science commissioning in a scale of a month and a half, perhaps two. The binning issue impact on the narrowbands needs to be still assessed to see if it's an issue or not. I'm assuming this is going to be happening as soon as after the interview comes and everything is going moving forward. Preliminary estimations from what I've heard here suggest an initial coverage rate of about 600 to 700. I keep pushing this number up in my head. So I'd say 600 square degrees per year for the science verification with all filters. If the unbinning is continued, the focus precision for dim sources gets worse by a factor of 2. Unfortunately, as Antonio pointed out. So this could be an issue in terms of survey speed. During the science verification, we need to, of course, reassess the survey speed, the fraction, possibly dedicated to what I call the blue inflation, with the blue filters, fast expansion rate. Fast turnaround science seeds suggested so far. Hectomap. Right?
Absolutely.
Okay. The North Ecliptic Pole, although I heard today 3 people independently coming with the idea that this would be an incredible, fantastic proposal for the open time as well, which could be actually deeper than Alexis, Raul, and eROSITA stars was pointed out by Ali, a particular region there, to provide more specifics about it. And please send more, more regions that you think are interesting, could optimize the science, a large area, fast return could provide. I filters to be observed at better than median seeing, the actual value to be defined, Eduardo plus the technical folks. And also, discriminatory power for cosmology with clustering 4 to 5 years. So it's interesting to have this out there. So those the main points that I get from this meeting, or some of them. The next steps that we have been discussing with Sylvia It's very urgent, is that we really need to reassess the manpower that we have soon, so that we have already a form, it's gonna be a little changed to pass to the whole collaboration, so that we know who do we have, for how long, how much they're actually dedicating. In principle, every member of JPAS should dedicate, one FTE every 3 years. And for us, it's very important to know what we have to be able to actually use the data that's becoming massively wisely. We plan to restart the PFIT, which is now going to be a JPIT. PFIT is a horrible name, right? But to remember what it is, it's very rememberable. I forgot. People that work dedicated to the accurate calibration of the data, and that get as a benefit for them, especially the early career people, temporary buildership for a number of papers, depending on what they do. Infrastructure team. Okay, JPAS infrastructure team. Used to be Pathfinder infrastructure. Right. And for the science working groups, it's very important to have lists, even if there are no official projects there yet, lists of potential science cases that you think of, even if it's completely off the main road. But today there was one already that was pretty interesting by Roy on trying to detect hypervelocity stars. Something that people didn't think before, and it's very nice. The more of these cases we have, the easier it is to manipulate and plan the targets that we can go. So for now, as usual, by tradition, next meeting, or at least a next meeting. We have discussed this in the CB, and I think people accepted even before I finished this invitation. But so there is one event, which is an eclipse, that will happen in October 14th, and Natal, which is the capital of Rio Grande do Norte in Brazil, which is a very nice place. I haven't been there yet, but I've seen many, many pictures. This is a few beaches there in the main place. And we thought that this could be a good opportunity to join the two events. Having a JPAS meeting physically there. And there are actually, I'm going to show you, there's a flight directly from Lisbon there. So in this beach called Praia da Ripa, which is about 40 minutes from the International Physics Conference Institute, which is apparently a very good, maybe Rolf can.
Yeah, it's a super nice building, and it's right next to a natural preserve and the beach. Nice.
All right. Of course, we have to apply, and now actually we're going to get an official invitation, but I think we probably make it. Fantastic. So, probably it would be very good to have that we had this arrangements like 9 months before, so we can get the tickets and get all the paperwork done before. So this is a flight, not necessarily the fastest, but there are flights directly from Lisbon. And yes, just I'd like to thank everybody for this meeting. It was great. Especially the organizers and those like Antonio, who is the one right here on the right. For making this reality, this meeting. Thank you. Sylvia, anything from your side?
It was not that bad. I just wanted to point out that a hybrid meeting is a technical challenge actually. In fact, I was quite afraid to have remote and local attendees and also remote and local speakers. But in the end, it went quite well. And the reason for this is the care and the dedication that the log has put in this. And in particular, Juan Antonio had to leave early. And also the chairs of the sessions that did all they could. I mean, all they could to stay on time. Okay, so my applause is for them.
He worked amazingly. I was very impressed.
Ahí no podemos sacar la
So,
It's okay.
all right.
Ciao. Bye bye.
Where's the camera?
Bye-bye, thank you.
Here, I think,
Okay.
in the middle of that.
Bye bye
thing.
everyone.
Bye.